Hi, Rachel. We hope you're feeling better. Wow, you know what? Today, guys, we are jumping into a new lesson, a new type of differential equation. You can see our learning target. I can solve exact differential equations. So, a little bit of review. We're going to have all these different types of differential equations this chapter. So we should go through a little process, a little order when we're looking at problems, because sometimes you're going to have to decide, which type of a differential equation you have and which method. You should always start by checking if, just like in the good old days of BC Calc, if you have a separable differential equation. Always check if you have a separable differential equation first. When you do, it's pretty standard. You've had a lot of experience with that. Second of all, if it's not separable, move to number 2. Say, hey, is this a linear equation of the form where, just like the last 2 nights, we were using integrating factors. Integrating factors, we'd get into standard form, and then we'd have e to the integral of p of x dx, and find that and multiply both sides by that integrating factor. Good things happen. But today we're going to say, well, wait a minute. What if there's a new type? What if we have m of x comma y dx plus n, a function of x and y dy, equals 0? What if we have that? This is known as an exact equation. And it's exact when not only do you have this basic format, but the partial derivative of m right here with respect to y would equal the partial derivative of n with respect to x. And if that seems oddly familiar, that's because what's driving this whole method is going back to multivariable calculus. And if you're looking at this, you're probably thinking, isn't that really Clairaut's theorem? Where you would say, in essence, take a look, here's the motivation that would be happening. Let's just say that you have a function of x and y, and it's equal to a constant. If we were to look at differentials, going back to our days in multi, take your derivative of f with respect to x times dx plus your derivative of y with respect to dy. Well, that would equal the differential of the function in general, and that would be 0 if we have c here. So this is really what's driving this whole thing. So this would be like your m, and this would be like your n. And Clairaut's theorem is more or less saying when you take the derivative of m with respect to y, you'd get the derivative of n with respect to x. If we get that, then you have an exact differential equation. So the question is, once you know you have an exact, what do you do? Well, first of all, you always check for exactness. You got to check that the partial derivative of m with respect to y does in fact equal the partial derivative of n with respect to x. Then we're going to focus on one of those functions, either m or n. I think a lot of times kids usually start here and they'll say, well, that m is really the derivative of some unknown function f with respect to x. And what we'll do from there is we will integrate. You can see if that were the case, assuming that we're working with the partial derivative of f with respect to x would equal m. When we take our antiderivative, we will now get a function m of x comma y plus a cy. Then we take our partial derivatives of y so that we can find that constant. Let's see this in action. I think this is going to seem very reminiscent of things that we did in multi first semester. So what is screaming out at us is we can take a look at our m and we can take a look at our n right here, and we can say, well, this sure looks like it very well might be exact. That's the basic format that an exact differential equation will have. But we should go ahead and check for exactness. We should go ahead and say, well, let's be real careful. Take that, number one, derivative of m with respect to y. How about we write it in this shorthand way, m sub y? I really like doing that. So if m is 2xy, what's the derivative of m with respect to y? What do we get? 2x. And let's do the same thing with n, but n, multiplied to this dy, we're going to take our derivative with respect to x. What's the derivative of x squared minus 1 with respect to x? 2x. These match. This is exact. So we can proceed. You could say, well, what do you mean proceed? Well, choose one of these, and usually it's m. And I'm going to say, look, I'm going to assume that m right here is in fact the partial derivative of some function f with respect to x. Breaking it down as a differential like we did in multi. You'd say, okay, well, what do we do next? Well, guess what? We're going to take an antiderivative. We're going to integrate with respect to x. So we integrate. What's the antiderivative of 2xy with respect to x? What do you think? X squared y. But you'd say, well, there's some constant. Well, remember, y's are thought of as constants in this regard, aren't they? So just like we did in our last chapter, if you think about it, if it seems like we did this recently in multi, we did. And you'd say, well, then I'm going to have this function g of y. Guess what we're going to do now? I want to find that g of y. I'm going to take a derivative. And I'm going to take my derivative right now with respect to y. I already was dealing with my derivative with respect to x. What's the derivative of x squared y with respect to y? What do you think? X squared. And what's the derivative of g of y with respect to y? G prime of y. And you say, well, why in the world are we doing that? Guys, that's what your n is. Your n would be thought of as the derivative of that function f with respect to y. Okay, everybody doing okay? So what do we do now? You can solve for g of y. We can look at this. Let me change the color up here just for a second. We can say, look, I can subtract an x squared from both sides. And that's all nice. And then I can say, well, g prime of y equals negative 1. I'm going to take my antiderivative with respect to y. And what would we get? What do you think? Antiderivative of this thing. We get negative y plus some constant. Right? Now, the cool thing is, what you just did is you found what g of y was. That's this thing right here. So I'm going to come back and I'm going to say, well, we're going to bring this f back over here. We're going to say, I know that f was x squared y, but my g of y is now going to be a negative y plus c, plus a constant. Now, your differential equation, you could write it in a couple different ways. You could say, ultimately, it was meant to be f of x comma y equals c, and we dealt with the differentials, setting it up to make that exact form. So a lot of times, what some kids will want to do is they'll just say, well, my f is x squared y minus y plus c, and you could equal 0. A lot of times, though, we just move that constant to the other side, and you don't even write it as a minus c. Most of the time, we just write it this way, ignoring the constant right here. But that's your solution. And that's how you solve an exact differential equation. We doing okay? Let's real quickly go to number 2 and I've changed the problem. So why don't you change it to, we're going to write 2x minus 1 dx plus 3y plus 7 dy equals 0. Obviously, here's my m, and here's my n. It sure looks like it's exact, but ultimately we need to check if it really is so. So I'm going to go to m, and what kind of a derivative will I be taking here? With respect to y. And m sub y, the derivative of m with respect to y is 0. Then I'm going to go to n, and I'm going to take my derivative with respect to x. 3y plus 7, take your derivative with respect to x. What do you get? Oh, wow. Clause's theorem is being validated right here. You'd say, well, that's what we'd expect to see, that our second derivatives with regard to a different variable would still hold. So how do we proceed? We could say, well, look, f sub x would be 2x minus 1. And now I'm going to take an antiderivative. What's the antiderivative of 2x minus 1? What do we get? Yeah, x squared minus x. Now be careful. G of y. You see, yeah, it is a constant in regard to x. But you see, f is really a function of x and y. So when I, get that general constant here, I'll say, look, it's some function of y. Guess where we're going next? We're going to take f and take the derivative with respect to y. And oh my goodness, what do we get when we do that? G prime of y, right? Anything with an x in it, when I take the derivative with respect to y, disappears. But what is f sub y? What is that really? 3y plus 7. And now we can go ahead and take a quick antiderivative. G of y would be, help me, what do you think? 3 halves y squared plus 7y plus a c, I guess. You could say, well, hey, now I know what that is. You could say f. A lot of times kids will just even drop the constant right here, but you could keep it there. It's definitely okay to do it. But the differential equation that you're asked to solve, generally we just move that constant over here because we're assuming that that was constant, and that's why the right-hand side of that differential equation would be 0. And we are done. Any questions?